For number 6, it wants us to use the second derivative to find the intervals on which f is concave up or concave down, and to identify any inflection points. So concave up, this is like the curvature of the graph. So if it's kind of curved upwards, it's concave up. If it's curved downwards, it's concave down. Concave up kind of looks like a smile, and concave down kind of looks like a frown. The inflection points of a graph, those are where it changes curvature from concave up to concave down, or vice versa. Now, potential inflection points, so if you look at the box above this question, potential inflection points are where the second derivative is equal to 0 or undefined. Exceptions would be that it cannot be undefined in the original function. Actual inflection points are if the second derivative changes signs on the number line at the potential inflection point, then it is an actual inflection point. And then, as always, to get the y values of that actual point, you would have to plug it into the original function. So let's get started. We need to find the first and the second derivative. So the first derivative, that is going to be equal to negative 4x cubed minus 6x squared plus 24x. And then if I take the second derivative, this is going to tell me negative 12x squared minus 12x plus 24. So my next step is I want to set f double prime equal to 0 for potential inflection points. I mean, this is kind of a very similar concept to when we set the first derivative equal to 0 for the critical numbers. Just this is the second derivative. So this is going to be negative 12x squared minus 12x plus 24 is equal to 0. And then if we factor out a negative 12, it's going to be x squared plus x minus 2 is equal to 0. We can factor that trinomial. That's going to be x plus 2 and x minus 1. So x is equal to negative 2 and x is equal to positive 1. These are the potential inflection points. So let's put those on the number line, very similar to how we put the critical numbers on the number line. Only this time we're going to be plugging in values into the second derivative. So if you want to use the table, you can put y1 as your second derivative, then go to the table. If you just want to plug in numbers directly into the second derivative, you can. Again, if you plug in negative 2 and 1 into the second derivative, it should be 0. It should confirm that. So if you pick a number that's less than negative 2, like negative 3 or negative 4, you should get a negative number. If you plug in a value between negative 2 and 1, like 0, you should get a positive number. If you plug in a number greater than 1, like 3 or 5 or a million, you should get a negative number. So concave up, the original graph is concave up where the second derivative is positive. So that's going to be from negative 2 to 1. And it's concave down where the second derivative is negative. So this is negative infinity to negative 2 and 1 to infinity. The inflection points, these are where it changes from either positive to negative or negative to positive. So If it just changes value, or changes sign, I should say, it's an actual inflection point. So at -2 and at 1, those are my inflection points. So to get the y value of these inflection points, you would plug these into the original function to get 48 and 9. So again, all of this is telling us about the graph of the original function. The original function is concave up from -2 to 1, concave down from -infinity to -2, and from 1 to infinity. And it changes inflection, or changes concavity, at -248 and at 1,9.